So let's talk about the notion of performance next. Performance is evaluated with respect to observable characteristics. These are things, observable, you can look at and measure. Usually you do it quantitatively. Things like response time, perhaps it's a survey of user satisfaction. It could be measures of resource utilization, how you're using that RAM and disk and CPU we talked about, or throughput, the number of transactions through the system measured as transactions over a period of time, number of requests served per minute, number of database transactions per minute, something like that. You can use qualitative measures, but usually I've seen performance is measured through things that are quantifiable and, again, observable. The classic measure is response time, right? Because this is directly tied to user satisfaction, right? Measured in seconds or milliseconds via some kind of client-server tool, which means normally you're hitting with some load tool against the server, against some endpoint. Data is showing that page fully loaded times vary a lot between mobile and desktop. And again, the fully loaded times refers back to whether I'm using the computer I'm recording on right now or something like my phone, whether or not the entire page comes down. Because remember, a full page load nowadays with client-driven applications typically means you're downloading part of a page and then making subsequent HTTP requests back to the server. One, to get content like images and other media. Another is to get scripts, your JavaScript and your CSS. And then the third thing is once the JavaScript is loaded and fires up and starts executing, it can make requests back to the server for typically additional content. There's a graph to the right. What it basically shows is that 3/4 of page loads happen in 5 seconds or less, half of them in 3 seconds or less, and 1/4 of them in 1.7 seconds or less. Of course, conversely, it means that 25%, I'm talking about this chart down here on the lower right, so we're talking about 5 seconds is right here, so it's roughly 75% of them, if you will, are to this side of the curve. That's how you read that chart. This is from a 2011 report that's widely cited. There's a 2017 report from Google that they put out, particularly as they were getting concerned about mobile page load times. The poor quality of mobile device viewing of the web is an increasing concern to mobile vendors because we still get a lot of our content from the web, not necessarily from proprietary apps. It concludes that the probability of a mobile user leaving a website increases to 32% once you reach 3 seconds waiting for the page to load, 90% at 5 seconds, and 123% at 10 seconds. So they're more than 2.25 times likely, roughly, at 10 seconds to leave. And that kind of goes, you think about how folks use this device nowadays. Folks tend to always be looking at it and doing something. If something's going to take a while, they're going to context switch and go to another app and do something, right? They're going to turn around and text. They're going to go on their social media. They're going to do. We're very transient users of our apps on phones. So if we can't load a page in, say, less than 4 seconds, chances are our website's useless from a mobile device standpoint. And one chart I didn't include on here is realize that mobile device consumption of web content is now outpacing all other forms, your desktop computer, your laptop computer, or whatnot. It's outpacing all forms, and the gap continues to widen. Though that kind of crossed a couple years ago as well, which is again why Google took a closer look at this in February 2017. Of course, in order to get performance measures, you need some kind of data collection and analysis environment set up. Performance is very sensitive to the operational environment in which it happens. So when you're going to baseline or internally benchmark something, realize that you have to take a look at the operational environment, which means both the clients that you have and the nature of the server. You can't just take some server in the corner and say, I'm going to performance test this, and then presume that if I just double the resources, I'm going to get double the performance benefit. That's a naive model. The opposite side of that is on the browser side, certainly the range of devices that we talked about last time, the nature of your computer, especially as we're using more and more of the computational resources on the client, is going to have a big impact on how fast that page renders, and also whether there's other issues. I mean, race conditions in JavaScript come up much more often on slower devices because you're more likely to encounter them in a non-deterministic way if there's a greater lag in loading the entire page. So even in the testing of things like our client-driven development in JavaScript, again, not the topic of this class. Maybe if you didn't take 421 with me, that doesn't make much sense. That isn't really what's important. What's important from our perspective in this class is that they are sensitive to the entire computational environment, the client resources, the server resources, as well as the network bandwidth in between. So typically you have this thing called a typical use benchmark, which means you kind of look at the average computer, right? You assume there's kind of a bell curve. You should know more about your server environment, your computational environment, but from a client side, you look and say, okay, what's the typical device here? And I'm going to presume that I have a relatively graceful bell curve formation around that typical device based on what the current devices are in the market, which is why folks are always going out to like Google's site and to Apple's site looking at what the current sales rate is of different devices at different levels based on the operating system as a crude way to kind of construct that typical client. A little drill down from performance. The fundamental concept is queuing theory, and we talked a little bit about bottlenecks before. We talked about Little's law, which we'll mention again right here, but talking again about this notion of your rendering pipeline. So if I'm starting at a browser, all right, and I'm making a certain number of requests from all the clients. This isn't just one client. This is from all of the browsers that are going over the internet to hit my front door. My front door is going to be some kind of networking device. It's a load balancer, firewalling type system. It may be an array of them. These all may be clustered, by the way. None of these tiers mean that there's only one of these. They're all going to be clustered, meaning and horizontally replicated in those things. So I'm looking at that classic N-tier architecture turned sideways in this. Queuing theory says I'm going to take a look at the ratio of requests that go from each one of these levels. All right. Now, why wouldn't they all be the same? Why wouldn't X star all be the same? Because not one is failures. Another reason though is not all layers need the same ratio of requests. So, for example, in Fielding's sense of the extensibility of the internet, maybe my organization before I go outside of my rendering box, maybe I have a caching proxy internally in my organization that I'm using, right? On the client itself, I have a browser cache that I could be using, right? So logically, a request can be satisfied right within the memory space of my browser by using the browser's cache. So certainly this is a simplistic model from a queuing perspective. My request goes out, it hits the load balancer, and then it hits a web server. Maybe this thing has static content that it serves, and a certain percentage of the requests are never going to get further than here. Then I'm going to go to the app server, and a certain percentage of the requests are served dynamically from my Tomcats, if you will, without ever having to go out to any middleware services, which may also eventually have to go out to the big database, right? So by the time I get to the percentage of requests, right, maybe if X0 is the total number of requests outside of my browser cache that were generated, maybe for every 100 logical requests, or maybe I do it in thousands because I can do 100 per page now, maybe for every 1,000 requests, the number of database hits actually is something like 3. Right, and maybe the number of dynamic requests out of my app server is only like 50, maybe 1 in every 20. I would want to understand that ratio when I do my capacity planning and I do my optimization. Where do I want to optimize to? Because I can always try and alleviate the tiers by either clustering and replicating these services or introducing new services in this chain to intercept more of the traffic. All right. The other part I want to understand is where the bottleneck can truly be, because I'll be measuring a delta time it takes on average to make it through each one of these. All right, so as I go through and measure that, So each one of these layers will have a different time associated with it, and then I can look at the ratio of these times, right? If this is time T1, T2, T3, and I plot a histogram of these, right? Maybe T1 is this time, T2 it takes this long, right? If this is magnitude of time on an x-axis, and I get to T3 and I say, wait a minute, my average requests on T3 are taking much longer. There I've identified my bottleneck, right? T4 and T5 can be over here. So I have too many of my requests taking too long is effectively one way to identify a bottleneck through an observable characteristics. Of course, another way to identify a bottleneck is through our scalability measure we talked about before in our process of profiling, meaning look at the amount of resources consumed and where a resource demand has reach beyond the limit of the resources available. In some ways, you can almost think of it as the difference between black box and white box testing, right? Black box was a functional, observable test of the functionality of a particular feature at a low level, the expected inputs and outputs, and treated as a black box. To a certain extent, we're talking about treating each one of these tiers as a black box and using the external measures of throughput or response time as a way to identify bottlenecks. White box actually goes inside the system and says who's consuming what, so I can predict where those bottlenecks are, even if I can't create a test today that forces the bottleneck to happen. Right? I want to call your attention to a common word that you hear, and that's performance tuning. All right. I mean, let me step back before I even say about tuning. The process of optimization is very broad. All right, optimizing could be reworking an entire solution, but implicit in optimization is usually we're going to try and stay with the same structure, which for us means the same architecture, and try and make each piece of it work better to try and increase the performance and scalability of the entire system. Tuning is a process optimizing each component in the architecture against expected traffic. So it's a post-architecture. I've already decided, misspelled that, but it's a post-architecture data-driven configuration architecture exercise. What that means is you've already made the purchasing decisions. You've laid out the software and information technology tiers of each one of these. You make capital investments. You're kind of, at that point, you've done the first step analysis to come up with the architecture. Now you're going to go through that architecture and try and make it as fast or as throughput oriented or as resource minimized, whatever that key performance measure is that you're optimizing against. You're going to try and tune. Tune means configure. It could be the number of database connections open. Could be the amount of memory you allocate to a JVM. It could be the amount of stack space within the JVM, that detailed. It could be the garbage collection algorithm that you choose in the JVM. It could be the maximum number of requests allowed into your HTTP server, and these kinds of things. You're trying to tune it so you're, again, optimizing against that particular area, if you will, or that particular component or that particular potential bottleneck, I should say. So I mentioned I'm already starting to talk about performance and scalability together, right? And they overlap, right? Better performance produces better scalability if performance optimizations reduce resource consumption. So I may be optimizing for throughput, I may be optimizing for response time, but at the same time, by doing that, I'm consuming less resources. Well, that makes sense. What if I'm minimizing the number of database round trip? I'm using less resources and I'm making the system run faster. Maybe I introduced a cache along the way or something. So I can solve both, but I want to make sure that performance and scalability, by the definitions we used, they are not the same thing, but they are highly interrelated, and very often techniques that will help you with one will help you with the other. All right. The second is, in general, if performance optimizations don't introduce errors at higher loads. Better performance produces worse scalability if the design optimizations introduce coupling. So if I start coupling things together, right? So I used to talk about this. If I wanted to write the fastest web response system possible tomorrow for this kind of system, I'd probably cut out the services tier here altogether. I might even cut out the app serve tier, and I put all the logic inside the database and stored procedures, right? It's stored procedures is code that executes in the same memory space that you're managing the data. So it's going to be faster because it cut out any level of indirection, network overhead, and so forth, and latency in the system that goes from X3 through X5 here and basically does it in one hop. Well, that kind of skip ahead is great from a performance optimization perspective, and I can guarantee you it will be faster. Problem is, now I'm tightly coupled because I've buried the code in a particular language for a particular runtime environment with all the features done together in a procedural language coupled with the database tables, which means I have no architectural flexibility anymore to maintain my code and evolve my code and make different decisions to optimize the system in different places. Right. So optimizations can require increased resource consumption in different places, and you have to be very aware of the typical footprint. That's where your profiling comes in. So, for example, when you introduce caching solutions, a very common thing to try and do, or some kind of pooling of resources, you realize that those things often hog resources. I'll give you an example of a pooling. In this architecture, when I talk between, like we had database examples where our Tomcat talked to a database, right? Typically, you have what you do here at this layer is you open up a database connection pool. You set aside a certain number of connections ahead of time. Now, what happens if, let me go here, what happens, so what I'm saying is I have horizontally replicated Tomcats, pattern 1. Let's say I got 4 of them. All right, and I have a big database here. The database has a physical maximum limit on how many connections that it can afford to have at any given point in time. In production and with Oracle, we used to use 10,000 connections at a time. My Tomcat server may consume a certain percentage of those, and I might say, okay, I got 4 of them, right? So I'm going to use 25% on each. So I'm going to give each of them 2,500. Or maybe I'll be safe and do 2,000 and leave a little bit left over. Well, what happens if I start introducing more Tomcats horizontally replicate here, and I don't realize that I need to adjust, and I start allocating more connections set aside ahead of time? Right now I'm starting to bottleneck this resource because these guys are all competing to keep their pools full, even if only a small fraction of this database connection pool actually uses the database at one time. These are complex provisioning and consumption scenarios that your infrastructure and your tuning process must be aware of at any given point in time, which is why you can't always just replicate or add more resources. You have to look at how those resources are shared in a shared resource infrastructure, which again gets us back to part of the point about problems with the monolith, if you will, and why it's not always the best thing. So anyway, performance scale we overlap. Performance and scalability tips. First is design for it. Component-based modular designs allow you to optimize for performance and dynamically allocate resources, which typically helps scalability. You got to spend time and plan to spend time tuning your application. Tuning can often result in tremendous gains in performance and scalability. Also, that process will often help you if you have fundamental limitations in your architecture. Maybe your architecture, maybe you've designed things in such a way and laid them out in such a way that no amount of tuning will get past them. You'd rather find that out in your testing and your experimentation environment than to try and find that out in production. And then finally, test for it throughout the life cycle. Include early stage profiling and analysis activities, create and conduct benchmarks at the component and system levels. There's kind of an old saying that goes that you optimize at the end. I've seen in my professional practice that optimizing throughout, or at least testing throughout and understanding what our resource consumption footprints and doing profiling activities early on in our initial sprints and not waiting for the end helped us to enforce early architectural decisions and ensure that they were the right ones instead of getting all the way to the end, hanging all these features off of a structure that was never going to work from a performance and scalability perspective in the first place. In the next talk, I'll talk about different types of testing as a form of wrap-up to this section.